Imagine a world where rocket engines are more efficient, reliable, and powerful than ever before. A world where space exploration is propelled to new heights, thanks to groundbreaking innovations by NASA. Rocket engines have been the backbone of space exploration for decades, propelling spacecraft and payloads beyond Earth's atmosphere and into the vast unknown of space. However, traditional rocket engines have their limitations, with issues such as low fuel efficiency, reliability challenges, and limited operating ranges. But now, NASA has embarked on a journey of innovation. If you're ready to learn the fascinating story of how NASA reinvented the rocket engine, then watch this video till end. Be sure to subscribe to and don't forget to hit that bell icon for regular updates. So let's dive deep into the video. NASA recently conducted tests on a 3D printed rocket engine that utilizes rotating detonation technology. This cutting-edge technology has the potential to significantly improve rocket fuel efficiency by up to 5%, which could have significant implications for space exploration and rocket capabilities. The rotating detonation engine works by utilizing supersonic flame fronts to generate thrust, resulting in more efficient combustion and increased performance. However, there are challenges and instabilities associated with detonations in rocket engines that need to be addressed. The recent tests conducted by NASA involved 18 runs of the rotating detonation engine, with a maximum firing duration of 113 seconds, and the results showed promising improvements in reliability, consistent thrust, and operating ranges. The successful development of rotating detonation engines could revolutionize rocket technology and have a significant impact on the future of space exploration. Let's delve into the science and engineering behind rotating detonation engines to see how they work. Detonation-powered engines are not a new concept and have been developed by the Air Force Research Laboratory in a heavily modified Rutan-Long-EZ aircraft. Unlike traditional rocket engines that use a continuous igniter to mix fuel and oxidizer, detonation engines use supersonic flame fronts to achieve combustion, known as detonation, which can produce more thrust with the same volume of fuel compared to deflagration, which is the combustion process used in most engines. However, initiating a detonation requires a large amount of energy, and for pulse detonation engines, like those used in the Air Force's test vehicle, the detonations need to occur rapidly, hundreds of times per second. Transitioning from deflagration to detonation is not fully understood and can be unreliable, but it is known that detonations are more likely to occur when the fuel is turbulent. Despite the challenges, detonation-powered engines have the potential to significantly increase thrust and fuel efficiency in propulsion systems. Challenges and instabilities of detonations in rocket engines. The use of detonation in rocket engines presents significant challenges and instabilities that must be overcome for successful implementation. One key challenge is the stability of the detonation process, which can be highly dynamic and prone to fluctuations in pressure, temperature, and combustion rate. These instabilities can lead to combustion issues, such as pressure oscillations, which can damage the engine and reduce its performance. Additionally, achieving consistent and reliable ignition of the fuel mixture to initiate the detonation wave can be challenging, requiring precise control of composition, pressure, and temperature. Controlling the propagation of the detonation wave in rotating detonation engines, which rely on the interaction of multiple waves, is also complex and requires uniform and stable combustion across the combustion chamber. Furthermore, the dynamic nature of detonations can create mechanical stresses and vibrations in engine components, risking structural fatigue and failure. Successfully addressing these challenges requires ongoing research, advanced combustion control techniques, and optimized engine designs. Overcoming these instabilities is critical for unlocking the full potential of rotating detonation engines and advancing rocket propulsion technology for future space exploration missions. Historical efforts to control detonations in rocket engines, such as the F-1 engine. The F-1 rocket engine, developed in the 1960s for the Saturn V rocket that powered the Apollo missions to the Moon, is a historical example of efforts to control detonations in rocket engines. The F-1 engine used a staged combustion cycle, which involved burning fuel and oxidizer separately before they mixed and burned in the main combustion chamber. Despite the technological challenges, engineers overcame combustion instabilities through extensive research, testing, and iterative improvements. The F-1 engine's complex design included precise control of fuel and oxidizer flow rates, temperatures, and pressures, as well as sophisticated injector designs and cooling techniques. These advancements paved the way for modern propulsion technologies, and the lessons learned continue to inform ongoing research and development efforts aimed at improving the efficiency, performance, and reliability of rocket engines for future space exploration missions. Advancements in material science and computational fluid dynamics enable NASA's test. Advancements in material science and computational fluid dynamics have played a critical role in enabling NASA's test of 3D printed rocket engines with rotating detonation technology. Material science has made significant progress in developing high-temperature and high-strength materials that can withstand the extreme conditions of rocket combustion chambers, including the high temperatures and pressures associated with detonation cycles. Additionally, computational fluid dynamics has advanced in recent years, allowing for highly accurate simulations and predictions of complex fluid flow and combustion behavior within rocket engines. Science and computational fluid dynamics simulations have helped optimize the design of the 3D printed rocket engine, including the injector design, fuel and oxidizer flow rates, and combustion chamber geometry, to achieve stable and controlled rotating detonation combustion. The synergistic combination of advancements in material science and computational fluid dynamics has enabled NASA to push the boundaries of rocket engine technology and successfully test 3D printed rocket engines with rotating detonation technology, opening up new possibilities for improved rocket fuel efficiency and future space exploration missions. Benefits of rotating detonation engines. Rotating detonation engines offer several potential benefits for rocket propulsion. One key advantage is improved reliability, as they have fewer moving parts compared to traditional rocket engines, reducing the risk of mechanical failure. Additionally, rotating detonation engines are known for their consistent thrust output, which can result in smoother and more efficient propulsion. Another benefit is the wider operating range of rotating detonation engines. They have the potential to operate efficiently across a broader range of altitudes, speeds, and atmospheric conditions compared to conventional rocket engines. This flexibility in operating range could enable more versatile and adaptable rocket propulsion systems for various space missions, from Earth orbit to deep space exploration. Overall, the benefits of rotating detonation engines, including increased reliability, consistent thrust, and wider operating ranges, make them a promising technology for the future of rocket propulsion, with the potential to revolutionize space exploration and transportation. Future implications of rotating detonation engines for space exploration and rocket technology. Rotating detonation engines hold significant promise for the future of space exploration and rocket technology. With their potential for improved fuel efficiency, higher thrust-to-weight ratios, and wider operating ranges, they could revolutionize rocket propulsion and enable new capabilities in space exploration. One major implication is the potential for an increased payload capacity, allowing for larger and more complex missions to be undertaken. The higher fuel efficiency of rotating detonation engines could enable longer duration missions, greater payloads, and increased mission capabilities, making them ideal for deep space exploration and interplanetary travel. Moreover, the higher thrust-to-weight ratios of rotating detonation engines could enable faster and more efficient interplanetary travel, reducing mission durations and opening up new possibilities for human exploration of distant planets and moons. Additionally, the versatility and adaptability of rotating detonation engines could lead to the development of more flexible rocket propulsion systems, capable of operating efficiently in different environments, such as in orbit, on planetary surfaces, and in low-gravity environments. In short, the future implications of rotating detonation engines for space exploration and rocket technology are promising, offering the potential for improved performance, increased payload capacity, and new capabilities in space exploration, paving the way for advanced rocket propulsion systems in the future. That's all for today's video. Thank you for joining us on this captivating expedition into the remarkable world of rocket engine innovation by NASA. We hope that you have enjoyed the video. If you have any question, feel free to ask in comment section. Be sure to subscribe to our channel and hit that bell icon for regular updates.